friends, we will see group of order 96 a little bit elaborately, and I will introduce something called group action technique. Group action technique that will help us to understand this 96, and this is most important and very useful in many contexts. Let us see how this counting method is not going to work, but this will work. Group action method. Okay, 96. Suppose a group of order I have a 96. 96 can be written as 2 power 5 into 3, right? 2 power 5 is equal to 32, and into 3 is 96. Okay, so we will start from the third Sylow's theorem. N2 congruent to 1 mod 2. As usual, N2 denotes number of 2 Sylow, number of 2 Sylow, and n3 congruent to number of, not congruent, just equal to number of 3 Sylow. Okay, so n3 congruent to 1 mod 3. This much we know, and n2 divides 3, but n3 divides 2 power 5, because we say that, right? Group of order p power alpha into m, and np divides this, not this, this just m. So better you see my videos to understand these things. I proved Sylow's theorem and I reviewed only statements and gave idea. Everything is available in my channel. Okay, fine. Now let's do it. 1 or 3, both are possible according to this. Now 1, 2, 4, 8, 16, 32, and you see this is not possible according to this equation, and this is possible. This is not possible. This is possible because 16 minus 1, 15 divisible by 3. This is not possible. So we are in a different situation, that like we have n2 and n3 situation like this. 1 16, 3 1, and 3 16, and you see that there is a problem here. The problem is, this is in the 56 there was a 7 Sylow subgroup which is big, but here we have 3, which is very smaller number, so we cannot do counting. Let's try the counting and you will see how this is fails. Let's take the simplest possibility where the Sylow subgroups are not unique. Let's take this and this. Okay, the simplest possibility is there. 3 and 4, I forgot to write it. The simplest possibility where n2 is 3 and n3 is 4. This is the simplest possibility. You will see the counting is not works. Okay, we will try to count. Okay, we will try to count from the prime number. So k1, k2, k3, k4. 3 Sylow subgroup are there. There 1 plus 2, 2, 2, 2. Here each and everything will contribute 2 order 3 elements and 1 for identity. But whereas you count from here, that is h1, h2 and h3. This is order 32. This will count for 31 elements from here, but this will contribute little bit, but we don't know how much intersection happens between them, so we have no idea what to do. And you see this is 8 elements plus 9, so 40 plus something, like under 50 only we are getting, but we are in 96. So we have to get a new idea to tackle this kind of questions, and that new idea is the group action method. You see where is the problem first started. The problem here, we have 3 possibilities, so we don't want to do anything, but we have here 1 possibility. Suppose n2 equal to 3, that means let's take x equal to h1, h2, h3, 2 Sylow p subgroups. Okay, Now I am acting G on this. As in the review of my Sylow's theorem statements, you will see we have a group action which is transitive action. That is very important because of second transitive action. Action is like this. We have a transitive action. Okay, this transitive action means we have a homomorphism from this to S mod x, that is in our case is S3. The order of S3 is 3 factorial, that is 6. Remember that we are 96 here, we are 6 here, so it cannot be injective. This not injective, cannot be injective. Okay, and as I said, the transitive action, the kernel, let's say this phi cannot hold G because transitive action. If it is whole G, that means any action, this phi G I give like this, phi G, where phi G from x to x, phi G of x is G comma x. In our case, phi G of hi, G hi G inverse, and everything is, let's say, ID map. That means G hi G inverse equal to hi for every G, at least h1, G h1 h2 inverse equal to h1. This says that for every G, this says itself that h1 is normal in G, but that is not true. We assume that this is not normal, so it cannot be identity map for every G. Okay, so the kernel is not full. So the kernel of phi is not trivial and not full. So this is normal subgroup. We know that, right? Every normal subgroup is some kernel of some homomorphism. Every homomorphism kernel is a normal subgroup. So this is the required normal subgroup, and hence group of order 96 is not simple. You know, because we proved there is a non-trivial normal subgroup and proper subgroup is there, and we proved this is not simple. So we are done. Okay, in the next video I will talk about order 12 and p square and q, which is very important, which uses the same idea. Okay, there also you can see the counting is not a really good idea to count, but it's very easy to use this group action technique. Hello friends, we are seeing applications of Sylow's theorem. In this video I wanted to talk about PQR group. Instead of that, I will give you the idea through 56. So it is advisable you to work with the same kind of counting technique for PQR. Okay, let's see. Sorry for the outer noise, I cannot control now. I wanted to use mic, but now it's not available. I cannot go outside, so please bear with me. Okay, let's go for 56. Okay, let's see group of order 56. 56 I can write like 8 into 7, that is like 2q into 7. Always you write like that, write like this. Okay, from small to above, powers also right here. Now I wanted to do the Sylow's theorem. As I said, we will start from the third Sylow's theorem. First theorem existence, that is fairly okay, but let's start with the third one. N2 congruent to 1 mod 2, where N2 denotes the number of 2 Sylow, N7 congruent denotes number of 7 Sylow. Okay, N2 congruent to 1 mod 2, N2 divides this 7. Similarly, N3 congruent to 1 mod 3, N3 not N3, N7 divides this 2 cube. Here 1 or 7, here 1 or 2 or 4 or 8. 1 2 2 square 2 cube. Yeah, fine. Now let's see, the 1 is always possible according to this thing. 7 is also possible, Here 1 is possible, 2 is not possible, 4 is not possible, because 4 minus 1 not divisible by 7, 2 minus 1 also not divisible by 7, but 8 minus 1 can be. So we have a situation like this: n2 is 1 or 7 possible, n7 is 1 or 8 possible. We got 1 1 is okay, right? 1 7 is also okay, 1 8 also okay, 7 it is not okay, because in 1 1 1 1 1 n2 and n7 1 1 we get both unique subgroups. So that says that is simple. The question is that order 56 is not simple. Okay, in the last video also I supposed to mention that we wanted to get a proper subgroup to say not simple, and here also I wanted to mention not simple. Any order PQ is not simple. Okay, so I wanted to say this is not simple. I want to give a proper subgroup which is not trivial, not full, and unique implies not trivial, not full here, because it's order 8, it is order 7. So we are done. 1 and 8 is also fine, because we are getting unique Sylow subgroup here. 1 here, 7 here is also fine, because we are getting unique subgroup here. So in the 3 cases we are fine. But when n2 equal to 7, n7 equal to 8, we are suffering. And I am saying that claim such thing never happens. How? Okay, this is how. Suppose, assume that such things happens, then we will start counting, because both are prime groups. This is very important. Both numbers are the 2 and the 7, and the 7 is very important, that is prime, and I wanted to count from there. Okay, let's list down this 8. Let's list down this 8 like this: k1, k2, k3, k4, k5, k6, k7, k8. I will count identity plus remaining how many elements? I have 6 elements, because order is 7. Then another 6 element will come from, because ki intersection kj is trivial when I not equal to j, because both are prime subgroup. If it is a non-trivial intersection, then that must coincide. Okay, so anyway, because of that, this will give 7, this will give 6, this will give 7, but I already counted the identity. This will give 6 6 6 6 6 6 because of the same factor 6. So totally I have 1 plus 8 times 6, it's 49. Now remember that I have a 2 this thing. I have a 2 let's say h1 and h2, 2 Sylow, at least 2 Sylow I will get, because 7 I will get anyway. I will get 2 Sylow. Then I will count from here. Already identity counted, then fine. Then this will give me 7 elements. How? Because order of this is 8, order of this is 8, and I already counted 1, and all the things are divisible by, the order is 2 powers, so this will give a 7. So 49 plus 7 is 56. But this is there, right? This has to give at least 1, because h1 is not equal to h2. This has to give at least 1 to this sum, so 57, but which is not possible, because we started with order 56. So hence we started with the order 56. This is not possible. So this case is completely false. It is not possible, and only these 3 cases will happen, and hence the proof. This is not simple, because I proved at least one of the Sylow subgroup is normal. Okay, next video I will prove about the 96. But the same idea you can use for PQR, and P comma Q comma R are primes, and P less than Q less than R you can use. I will prove about PQ in the next or some other lectures, because which is needed, and also order 12 I will talk about. But you try to prove the same counting idea, it will exist. If you assume that not all of them are unique, everything is not unique, then you will get some over counting. The same idea you can do it. Okay.